Jai Hind, myself Pushkal Shukla, Assistant Professor in Computer Science Department at Akgec Engineering College, Ghaziabad. Today I will deliver lecture on theory of automata and formal language. The topic is of finite automata, and this topic is helpful for the BTech 4th semester students of executive and competitive examination like GATE, PSU and etc. So theory of automata and formal language, finite automata. So the objective of this topic is to make the students able to understand the requirement of finite automata and design and implement a finite automata with the corresponding languages. Now, what is finite automata? First, we have to understand what is automata. So, automata is a machine. It is a plural of automation, automata. It is a Greek word. It means ki automata means self-acting. So, automata is a self-acting propelled device which takes inputs and provides outputs without the intervention of human beings, just like a vending machine. There is no temporary storage. Only takes inputs and provides outputs. For what actually simple automata does, this is a CPU, this is an input given, and correspondingly we get output. And there is a program, there is a memory that program are stored, and there is no temporary memory. This is a temporary memory. So initially, when computer came into existence, it generally takes the inputs, process it, and then provides outputs, and there was no storage concept. So just like as a vending machine. So automata is a simple machine, abstract model which takes inputs, provide outputs without the intervention of human beings. So what is a finite automata? It is a mathematical model that works for several computer algorithms. It is called finite automata, as we know. It is called finite because it works on the finite set of input symbols and finite number of states are there. So if automata has finite number of input symbols, finite number of input symbol on the input alphabet, input tape, this is just like as this. This is the input symbols. This is stored on the magnetic tape. So finite number of input symbols and finite number of states. States are controlled by the finite control machine. So therefore, it is called finite automata. Here we see a block diagram of the finite automata in which magnetic tapes are there. Magnetic tapes are divided into the different squares, and each square is capable of having one symbol at a time, and there is a finite control system which controls the states. Initially different states are there, Q0, Q1, Q2, Q3 up to Qn. So for example, any states are there. In Q0 is said to be initial state, then Q1, then Q2, then Q3, and the last one is suppose Qf. So these are the states, and these states are controlled by the finite control machine by reading head. Reading head is there for scanning the input symbols that is to be there in the magnetic tape, and correspondingly output is produced. So there are two types of finite automata: deterministic finite automata and non-deterministic finite automata. Firstly, before discussing about finite automata, we see general automata. So automata can be distinguished by their temporary memory too. So finite automata is a machine which having no temporary storage. That is very simple machine which is used for the computation purpose. Second type of machine is known as the automata, is known as the push down automata. So push down automata is a machine which takes inputs, provide outputs. There is a temporary memory. Temporary memory are used for the calculation purpose actually. So what actually, suppose we have to perform like function fx equal to x square plus 3. So for this calculation, there is a program memory where instructions are stored. So how it can be stored. Just for example, y equal to x into x and fx equal to y plus 3. Some instructions are retained in the program memory. This is the part of the program memory. This is input, this is input, and there is a output, and it is a CPU. Again there is a temporary memory. So what temporary memory do? Temporary memory, suppose we have to perform this function fx equal to x square plus 3. So fx equal to x square plus 3. So suppose x equal to 5 we pass. So what temporary memory does? The value is going to calculate in this temporary memory fx equal to 5 into 5 by this way. So y first calculate y equal to 5 into 5, that is 25, and fx equal to 25 plus 3, that is 28. So this type of calculation is done in the temporary memory. So there is a special type of temporary memory that is known as a stack, is also present in the PDA, push down automata, and this stack is useful for like pushing the operation and popping the operation, push and pop operation. We use a stack. Another type of automata that is known as the Turing machine, which having a random access memory. So by this way we can distribute based on the temporary memory like finite automata, PDA and the Turing machine. And if we are talking about the capabilities of the machine, so we see a finite automata is less than the PDA, is less than the Turing machine. So Turing machine is more powerful and it is much useful. Then we come on the point finite automata. So finite automata we can divide into the two types like deterministic finite automata and non-deterministic finite automata. DFA, now come on the point DFA. Deterministic finite automata, for a DFA the machine moves to a particular unique state for a given state and a given input. That's why it is called deterministic. As we see, a finite number of states and number of input symbols are there, that is finite. Deterministic, because of every DFA the machine moves to the particular unique state. For a given input and a given state. So here we see for a given state Q0 and for given input A, it goes to the particular state Q1. So we can write it through the transition function, like this is a delta which represents a transition function and current state is Q0 and input given is A. So it goes to the fixed state Q1. So the path of the machine from the current state and the current input, it is fixed. It will go to the Q1. It is a deterministic. Another example we see a deterministic finite automata, just like hands of a clock. It always move in a clockwise direction, right? Clockwise direction. So it is fixed. Another example that is non-deterministic, the human hands. It cannot be fixed. It depends on moods and thoughts of the human. So it is not deterministic. It is not deterministic. It is non-deterministic. So if the particular state and the particular input, if it moves to the particular state, so we can say that this machine is a deterministic finite automata. That's why it is called deterministic. As the number of states in a DFA and the number of input symbols on the input tape is finite, that's why it is known as deterministic finite automata. Here we see for the given state Q0, and if we provide a output B, it goes to the state Q2, that is fixed. So that's why it is a deterministic finite automata. Mathematically, deterministic finite automata is a 5 tuple, yeah, quintuple. This 5 tuple is quintuple. A deterministic finite automata is a quintuple. 5 tuples are there, 5 variables are there, and these variables are, suppose this is a DFA, Q, sigma, delta, Q naught, and F. There are 5 variables, 5 tuples are there, and every tuples having its own meaning. Q is a finite set of states. It is a finite set of states. This sigma is a finite set of input alphabets. Transition functions, this is delta. Delta is from mapping from, it is a transition function mapping from Q into sigma to Q. Q naught, this Q naught I am talking, Q naught. Q naught is a element of Q, that is initial state. F is a subset of capital Q in a finite set of states, is a subset. That is also known as the accepting state of final state. In DFA diagram, in a diagram, the accepting state or final state will be denoted by double circle or double loops. An initial state will be represented by a single circle marked with arrows like this. This is a presentation. This is a representation of initial states and the final states in diagram. So here we see tuples one by one through the examples. For example, this is a state Q naught. So this is a, so if we are talking about tuples M, Q, sigma, delta, Q naught and F. For this diagram, for this DFA, the Q is, the states of this DFA is Q, Q naught, Q1 and Q2. So this is Q, this is Q. Input alphabet, sigma equal to the inputs given to this DFA, that is 0, 1, 0, 0, 1, 1. So input is 0 and 1. Transition function is important for DFA. It is a representation, it is the way of representation of the DFA, it is a method by the transition functions. We can represent DFA by 3 ways: representation through transition diagram, transition tables and the transition functions. So we are talking here just transition functions. So transition functions, so how we will represent this DFA through the transition function. So we write sigma delta Q naught and input is given 0, so it goes to Q naught. Again transition function, that is Q naught, and we provide the input as a 1, then it goes to Q1. Then Q1 0, so Q1 0, it goes to the Q2, and Q1 1, it goes to Q naught. Delta Q2 0, it goes to Q2, and delta Q1 1, it goes to, no sorry, Q2 1, Q2 1, it goes to the Q1. Initial state Q naught. So here initial state is Q naught. So initial state Q naught, initial state Q naught, and the final state F equal to, this is a Q naught. So initial state Q naught equal to Q naught. We write this, and the final state, that is double circle, that is Q2. So by this way we can represent a deterministic finite automata. So by this example we see the significance of the each variable, and we write each variable like this. Now representation of delta, representation of DFA talking. So transition diagram. So this is the example of DFA through the transition diagram. This is a transition diagram. So Q naught diagrammatically we are going to represent here. So every states can be represented, simple states can be represented by the single circle, and if it will be the initial state, then it will be marked by arrow, and transition will be shown like this, This is the transition actually, this is a transition, then this is the intermediate states, and this is the final states. If double circles are there, then it is said to be a final states. So this is a transition diagram of the DFA, that deterministic finite automata, and we see here this is a deterministic because for every given state and the given input it goes to the fixed state, particular state. So that's why it is known as the deterministic finite automata. By the transition table, how we represent it to the transition table? So first of all we write here a present state and then the next state. So present state is Q naught, Q1, Q2. These are the three states. So we write here like Q naught, Q1 and Q2. Next state, after two inputs are there, 0 and 1. So we write here a 0 and 1. After giving Q naught, after taking a Q naught as a current state and current input is 0, for this we goes to the Q naught. So by this way Q naught is the current state and 0 is the input given, then it goes to the Q naught. Another Q naught is the present state and 1 is the input. Q naught is the present state and 1 is the input given, so it goes to the Q1. So here see, Q naught is the present state and 1 is given input, then it goes to the Q1 state. So by this way we can represent through by the transition table. Here we write arrow on the initial state, so arrow is marked here, and the final state will be represented by either double circle or marked as a star. So here star, both representations are there. If we mark star on any states, then it will be treated as a final state. Yeah, we mark as a circle on this. So Q2 and mark it as a one circle, then it will be treated as a final state. Both representations are there. Then third representation by which DFA can be shown like transition functions. So here we see through the transition, this is the way of transition functions. This is a way to represent through the transition function, already discussed through the transition functions. Now examples, we see the examples of the DFA. So here we see Q naught, three states are there, Q naught, Q1 and Q2. So and alphabets, input alphabets are 0 and 1, only two alphabets are there, 0 and 1. So alphabet sigma equal to 0, 1, and the start state here is Q naught. Here start state, yeah, initial state is Q naught, and total states are 3. This is not a start state, this is a total states. In Automata, DFA is Q0, Q1 and Q2. 3 states are there. And the initial state or start state is Q0. And the final states are those states which are made by double circles, that is Q0 and Q1 is the final states. And the most important thing is a transition function, that is delta. On transition functions, we write like this: 3 states are there, Q0, Q1 and Q2, and 2 inputs are there, 0 and 1. So we see here for state Q0 and provide input as a 0, it goes to the Q0. So Q0, if you provide input 0, then it goes to the Q0. For Q0 and provide input as a 1, it goes to the Q1. So Q0 provide input as a 1 goes to the Q1. Similarly, for state Q1, for provide input 0 goes to the Q2, Q1 input is 0, Q2, and Q1 input is 1, then Q1. Q1 input is 1 is Q1, goes to Q1. Similarly, for particular state Q2 and provide input 0, it goes to the Q2, and 1 also it goes to the Q2. And here we see a Q0 and Q1 both are the final state, so we mark here as a star, Q0 and Q1 both, and this is also an initial state, so write Q0 like this, Q0 like this. So this is the way to represent DFA. This is the way to represent DFA. So language of DFA. The language of DFA, M equal to Q, that is states, finite number of states, finite number of input alphabets, transition functions, initial states and final state. This is a tuples of DFA. So the language of DFA is the set of all strings over sigma accepted by M, it means LM. LM and is denoted by LM equal to W, and W is a string taken over from the sigma star. So W is a LM equal to W, and W is an element of sigma star such that transition function Q0 to W goes to the final state, where QF is element of F. Just for example, we can see this example like electric switch. So electric switch, there are 2 states, off and on, and off state, if switching the flip the switch, it goes to the on state, and similarly at on state, if flip the switch, it goes to the off state. So there are 2 states, off and on, and the language of M is, this is the final state and this is the starting state. So the language accepted by this machine is F, it goes to the final state, then F, again F, then F, 5 times F, like this. So this type of language is accepted by this DFA. So we can write here as Fn equal to N such that N is a odd, because this type of machine can accept language F, triple times F, 5 times F, then 7 times F, and so on. So we can write here L equal to F ke power N, where N is odd. So this type of language is accepted by this DFA. Thank you.